In the previous video, we saw an algorithm for TSP that's not guaranteed to give you an optimal solution, right? The nearest neighbor algorithm. Uh, we know this because we found a counterexample. Okay, so how about a correct algorithm for TSP? And so it turns out that one way to do this is through what's known as an exhaustive search. And the idea, as you might expect, as the name suggests, is that you just try all the possible ordering of points, every single one of them, and then pick the one that minimizes the length of the tool, right? So again, that's my English description up on the slide, and below it here is the pseudocode description, right? And so the idea is you are trying to find the minimum of n factorial numbers, right? Because that's the number of permutations we have here, right? If I have n points, I will note parenthetically that you do have a worksheet associated with this, which will help develop some of this for you. And so the idea is we try each of these n factorial permutations of the n points, and you compute the cost of each permutation, and then you use the variable d to keep track of the minimum you found so far, right? And each time you find something better, you update d, and you update p sub min, which is the winning permutation, right? So that's the algorithm. Now, precisely because the algorithm considers all orderings, you're guaranteed an optimal tool. I mean, this does not require a complicated proof. Okay, it's pretty obvious this is going to give you a correct answer. The problem is that it's potentially extremely slow. And so let's explore that idea. So let's do this thought exercise. We're going to attempt all n factorial permutations, okay? How about if we assume that each permutation can be evaluated in a single clock cycle, on a 1 terahertz processor, okay? So let's give that a crack. Well, what is a terahertz? So let's maybe get some of our numbering straight here. Okay, so see, where am I? Okay, so kilohertz would be 1,000, right? Megahertz would be 1,000,000, so 10 to the power 6. A gigahertz would be 10 to the power 9. And the next one here is terahertz, and so that's 10 to the power 12. Okay. So this means you are running you're running a trillion operations or a trillion clock cycles per second, okay? So yeah, let's do this analysis, keeping that in mind. Now, I hope you agree that this is an impressive processor, right? So, I mean, how many of us have terahertz processors on our laptops, right? We don't. And so this is a very impressive computer. Not just that, I'm assuming that it takes a single clock cycle to evaluate a permutation. Now, in fact, it's going to take a little bit more than that in practice, because to evaluate a permutation I have of length n, I have to add n numbers, right? And you could reasonably expect a single addition itself to take a clock cycle. So we're looking at like maybe n clock cycles just to evaluate a permutation, but we're being magnanimous here. Okay? We're assuming that all you need is a single clock cycle to evaluate a permutation. All right, so to think about this some more, let's get hold of a calculator. And so, okay. So here's my calculator. This is being a bit sluggish here. Okay, I think we have it. All right, so what I have here is 30 factorial, right? So I mean, we are assuming, and let me just do this for your benefit. Okay, so I want to compute 30 factorial, and so indeed this is the answer. So why 30? Well, 30 is not an unreasonable number of packages you might want to develop to deliver in a day, right? So this is what you're looking at in terms of the number of permutations. Now, each permutation can be evaluated in a single clock cycle, and a clock cycle is in a 1 terahertz machine is 10 to the minus 12th of a second. Okay, so the number of seconds it's going to take is what I get if I divide this by, let's crank out all the zeros. So that's 3, 6, 9, 12. Okay, I mean, in reality, you and I know that what's going to happen here is that the 32 here will just drop to 20, right? Because we're dividing by 10 to the power 12. So let's do that. And so in fact, that's what we have. Now, this is the number of seconds, okay? So we should divide by 60 to get the number of minutes, okay? And then divide by another 60 to get the number of hours, and divide by 24 to get the number of days, and then divide by 365 to get us the number of years. And so we're looking at in excess of 8 trillion years to actually do this, okay? So I hope you agree this is not a worthwhile strategy. If you actually think about it, if I have 30 packages to deliver, I'm probably better off just going ahead with a suboptimal route, just figure this out sort of heuristically on my own and just go deliver the 30 packages. The optimal algorithm here will still be chugging away long after I'm done delivering the packages. And so that's the main idea here. Now, let me pull up my slides again. Okay, so yeah, we've done this analysis, right? And we've seen that this is an exceptionally long amount of time. And so it is an extremely slow strategy. Now, I'm asking a couple of questions here. You probably noted when you did the worksheets, and I think your example there had an n equal to 4. You found that because of the cyclic nature of this, that there really aren't n factorial, distinct tours. It's actually n minus 1 quantity factorial. And so, I mean, but honestly, is that much of an improvement? Because if I'm doing 30 factorial and then I divide by 30 because my number of distinct tours is actually n minus 1 quantity factorial, well, I'm still taking that huge 10 to the power 12 number and dividing by 30. So it's still going to be pretty bad. On a small example like the one you did in the worksheet, this in fact makes a difference because it brought you down from 24 to 6. You can also then argue that if I do a tour in one order and then I do the same tour in reverse order, that it's actually the same thing. And you would be right. And so, but that means you can divide by another 2. And so honestly, you're still looking at a very expensive proposition over here. All right. And it turns out that at this point of time, no one has discovered a correct algorithm for the TSP problem that's also efficient. Okay. And that is the situation here. We will later find as we progress through the semester and end up with NP completeness that the TSP problem is an example of what's known as an NP complete problem. And there are many such problems for which no one has discovered an efficient and correct algorithm. In the meantime, we will spend most of the semester on problems that actually have solutions that are both correct and efficient. All right, so when we come back next time, we will actually begin a new chapter on complexity.